Alright, in this video we're going to look at linear approximation and its applications. First we're going to look at linearization and then we will look at linear approximation. So linearization is the idea to use the tangent line to find out more about the curve itself. And the idea here that linearization is based on is the idea that when you zoom in a whole lot on the graph of a smooth function at some point, if the function is smooth, then the tangent line and the curve start looking very similar. They're almost the same. The closer you get, the more you zoom in, the more the tangent line appears to look more and more like the curve. So the idea behind linearization is to use the tangent line to the curve at a point P to approximate the value of the function at points near P, since they're so close. That's the idea. Since the tangent line and the curve are so close to each other, when you get close enough into P, you can use one to approximate the other. And here's a little graphic of a smooth curve, and we're going to zoom in on this point P, and you can see that as you get pretty close, the tangent line and the curve are nearly identical. So if we want to evaluate a point on the curve, maybe say over here a little bit to the left of A or a little bit to the right of A, and maybe the function itself is rather difficult to work with, you can approximate the value of the function by just plugging into the equation of the line, by using the equation of the tangent line. And then you can say, well, they're close enough, right? As long as your y value is close, or your x value is close enough to A, you can assume that your y values will be close enough to each other. Now here is a curve with a sharp point. Now it does not make any sense here. As we zoom in on the sharp point, for one, there really is no tangent line, but no matter how much you zoom in, the y values near A there's no way to approximate the y values of the function by just getting close to A, because there's no tangent line, there's no smooth curve. It doesn't make sense. So the function does have to be smooth. Okay, so what we're going to do is assume that the function f is differentiable on an interval containing a point A, and then the slope of the tangent line to the curve at the point A comma f of A is f prime of A. So therefore the equation of the tangent line is in point slope form, y minus the y value at that point, which is f of A, is equal to the slope, which is f prime of A at A, times the difference in the x values, x minus A. So that's the point slope form equation of the line. If we solve that for y, we get y equals f of A plus f prime of A times x minus A. So the linearization is simply the equation of that tangent line. That's all it is. The idea is we're going to approximate f of x by the equation of the tangent line, which I'm going to call L of x, which is given by this. The equation of the tangent line at A is equal to f of A plus f prime of A times x minus A. Now what we're going to do is use this linearization to approximate the value of the square root of 1.1. Now the idea here is maybe you don't have a calculator, and keep in mind these techniques were developed before calculators were so common and affordable. Okay, so it would have back in the day been quite a bit more difficult to actually approximate this value, so this would have been a pretty useful method. Alright, so the idea is that 1.1 and 1 are pretty close together. Now the square root of 1 is easy to take, so we can rather easily find the equation of the tangent line to f of x equals the square root of x at x equals 1, and then you can see from the visual here, say, well, 1.1 is close enough to 1, we're going to approximate the function value f of 1.1 by simply plugging into the equation of the line, which without a calculator is much easier to do. Okay, so we're going to first find the linearization of f of x equals the square root of x. So we're going to need its derivative. So if f of x is equal to the square root of x, let's write that as x to the 1/2. So then its derivative by the power rule is 1/2 x to the negative 1/2. Okay, and we actually don't need the general derivative. We need the derivative at a, which is 1. Let's make a note of that. This means a is 1 right there. Okay, so we need f prime of 1, which is 1/2 times 1 to the negative 1/2. And perhaps we should write that as 1 over 2 times the square root of x. So plugging into that, square root of 1 is 1, so we get f prime of 1 is 1/2. So the slope of the tangent line at x equals 1 is 1/2. So then we need f of 1 as well. If f of x is equal to the square root of x, f of 1 is the square root of 1, which is 1. Okay, so I'm going to plug into this linearization line right there. So we can say f of x, at least for x values near 1, is approximately equal to L of 1, that's just the equation of the tangent line, which is f of 1 plus f prime of 1 times x minus 1. Oops, we should call that L of x, not L of 1. So it's the equation of the tangent line in terms of x. There we go. F of 1 is equal to 1. F prime of 1 is 1/2. Multiply that times x minus 1. And we can simplify this. So we get, distributing the 1/2 here, we're going to get 1/2 x, and then we'll have 1 minus 1/2 is positive 1/2. So the equation of the tangent line at 1 is given by 1/2 x plus 1/2, which I know was on the graphic right there, but that's how you get that equation. Now we can say, yeah, 1.1 is probably close enough. We're estimating that. To 1, to say, well, f of 1.1, or in other words, the square root of 1.1, can be approximated by the equation of the tangent line, or the value of the tangent line at 1.1. So if we plug 1.1 into here, we get 1/2 times 1.1 plus 1/2, which, if you calculate that out, comes to 1.05. So the square root of 1.1 is just a little bit more than square root of 1, which is what you would expect, or roughly 1.05. Now, just for comparison purposes, let's see what the actual value of the square root of 1.1 is, and we will see how close this is. So let's do 1.1. We're going to take the square root. Okay, the actual value of square root of 1.1 is 1.04880884. Let's go with 1.0488. But this is the approximated value that we were looking for. So actual value is 1.0488. Pretty close to 1.05. Okay. Now, using that same linearization, let's use that to estimate the value of 0.1. Now, this is obviously going to be a little bit off, because if you come up here to this picture, 1 is here, 0.1 might be right about in there or so. So you can see there's going to be quite a bit of error, and that's really just what I want to illustrate here. Okay, so if we try to use the same linearization, so we're going to use this function L of x right here to approximate the value of 0.1, and this is really an inappropriate approximation to use, but I want to show you what happens. So L of 0.1 would be 1/2 times 0.1 plus 1/2, and that's going to come out to 0.55. Okay, so let's do the actual square root of 0.1 to see what this actually comes out to. We'll see how far off that is. So let's go with 0.1, take the square root. Actual value is 0.3162, roughly. So I would say that's a pretty bad approximation, very far off. So what would be a better value of A to use to approximate 0.1? Well, you want to pick an x value for A that is close to this x value of 0.1, but you want to pick a value of a that's easy to take f of. Easy values are f of 1, because the square root of 1 is 0. 0 is much closer to 0.1, so square root of 0 is 0. That's much, much simpler to use. So for this question, what value of a would work much better? I would say a equals 0 would work better. Now we already have the derivative of the function up here. F prime of x is 1 over 2 times the square root of x. So let's actually compute the linearization at 0 and see how much closer we get. Okay, so f prime of 0 would be right here, 1 over, where are we? 1 over 2 times the square root of 0. Of course, that's not going to work because you can't divide by 0. Which makes sense if you think about it, because the square root of x, f of x equals the square root of x, is only defined for x greater than 0. So that's the first x value at which it's defined. And you can't talk about the slope of a tangent line at an end point of an interval. You have to have some y values over here. Even if we did, I suspect it would have a vertical tangent line. Okay, so what would work a little bit better? In other words, what's another number that's close to 0.1 that we can compute the square root of pretty easily? And you want to think about perfect squares here. So maybe, like, think 1 squared is 1, 2 squared is 4, 3 squared is 9, which means, what if we chose a to be 0.09? Because we can take the square root of 0.09 rather easily, right? Because that's very close to 0.1, and we can do that square root. Okay, so let's try this one instead. So f prime of 0.09 is 1 over 2 times the square root of 0.09. And so we have 1 over 2 times, let's see, the square root of 0.09. What number squared equals 0.09? That would be 0.3. 0.3 times 0.3 will give you 0.09. So that's 1 over 0.6. I'm going to leave it like that, actually. Well, no, actually, that's not good. Let's go ahead and write that as a fraction. Why not? Okay, so 1 over 0.6, that's 1 over 6 tenths. So if you flip that, that's 10 over 6, or 5/3. Okay, so that's the derivative at 0.9. So then if we want to compute the linearization at 0.9, let's write that first. That's a bad approximation. Okay, it's coming back down here to the linearization. No, actually we need to recompute that. So L of x, this is with a equal to 0.09. We do need to label because all of your equations here we're calling L of x for all the different values of a. So this is the L of x for a equal to 0.09. Is f of a, so that would be square root of 0.09 plus f prime of a, we just computed, is 5/3 times x minus a, x minus 0.09. Okay, so plugging all this in, square root of 0.09 is 3/10, 0.03. We get, let's see, oh, let's plug in our number. We want to find L of 0.1 is what we're trying to approximate here, is f of 0.1. So plugging in 0.1 for x, then we have 3/10 plus 5/3 times 0.1 minus 0.09. And if you calculate that out, you're going to get 19 over 60, which is approximately 0.3167, which is a much better approximation to the actual value of square root of 0.1. And on that note, if we wanted to use this idea of linearization to estimate the square root of 0.18, what might be a good choice for a? Well, you would want to choose an a that's close to 0.18, but that's easy to take the square root of, both for the purposes of the derivative and for this f of a value. So a perfect square that's close to 0.18 would be 0.16. So I would use a as 0.16, right, because 16 is a perfect square. So we could calculate that relatively easily without a calculator. In this next example, we're going to find the linearization to f of x equals sine x at x equals 0. And we're going to use that to approximate sine of 2.5 degrees. Now, if you think of degrees and radians, 2.5 degrees is actually pretty close to 0. So this will be a pretty close approximation here. So let's see. Okay, so let's first find the derivative. So the derivative of sine of x is cosine of x. And then we can construct the linearization, and this is for x is 0, or I'm going to call it a is 0 actually, because x is something different. X is the x value near a. So this is the linearization at a equals 0. That's what that is. Okay, is f of a, which would be f of 0, plus f prime of a is f prime of 0, times x minus 0. So x is the x value near a, so I leave that as x and plug in a here, here, and here. Okay, so f of 0, that's sine of 0. Sine of 0 is 0. F prime of 0, that's cosine of 0. Cosine of 0 is 1 times x minus 0. This is just simply x. So at a equal to 0, the equation of the tangent line is y equals x. Okay, which you can see on the graph there. It's a pretty close approximation. So if the x value is close enough to 0, this could be a good approximation. Well, before we can work with this, we have to convert degrees to radians, because radians are a pure number that are unitless. So let's go ahead and first convert 2.5 degrees to radians by multiplying that times a conversion. I'm going to go with pi radians over 180 degrees. And then my degree units cancel. And that's going to come to 2.5 over 180 comes to 72. So this is pi over 72. Technically there's no unit, but you can write rad for radians if you want. And if you approximate that, that's about 0.04363 radians. Okay, so 0.04 is pretty close to 0. All right, and let's zoom in on the graph here and see what happens. So if a is equal to 0, oops, should move that. A is 0. Get that back there. Okay. Now there's our x value, and as we move it in, there we go. As we move that x value in closer and closer, you can see that since the linearization is the x itself, L of x equals x, the y value is actually right at equal to the x value. Let's do this at 2.5 degrees. Goodness, it's so close you can't even hardly tell. The value of a, or x, at 2.5 degrees is 0.046332. So that is approximately equal to sine of 2.5 degrees. The y value is roughly equal to the x value since L of x equals x. They're just right on top of each other. It's a very close approximation. Okay, so since L of x is x, I'm going to write this out. We can say the square root, not square root, sine of 2.5 degrees, or in other words, sine of pi over 72 radians, is roughly equal to L of pi over 2, it's pi over 72, but L of pi over 2 is pi over 72, which is the exact value, or the approximated value of sine of 2.5 degrees is 0.04363. Okay, so very small error there. And that brings us to differentials, or using linear approximation in a slightly different way, which is to estimate the effect of a small change. So the question here is, if x changes by a small amount, what does y approximately change by? And it's illustrated rather clearly by this picture, and we're going to write it all out as well. So going back to linear approximation, so the linearization at a value of a approximates a function f of x. So we can say f is approximately equal to its linearization at a for x values near a, which is f of a plus f prime of a times x minus a. Okay, so a is a fixed point and x is some point, x is something nearby a. We should write that out. So where a is your fixed point, it's actually down here. Meaning it's not moving. And x is near a. Okay, so if I subtract f of a from both sides, we get f of x minus f of a. It's approximately equal to, the approximation sign is important, f prime of a times x minus a. Okay, so let's reinterpret this a little bit. So this actually down here should say a. Let's call that, mark that out a little bit. Let's call that a. Let's call this x. That's a better way to do this. Okay, so delta x or dx, those are both ways of indicating the difference between two x values. So this x minus a, that's this minus this, gives you both delta x and dx. They're the same. We're going to call it delta x right there. F of x minus, oops, I wrote that wrong, f of a, subtracted f of a from both sides. F of x minus f of a is the difference in the y values right here. Here's f of a, and f of x is that value in the black dot right there, right? That's the f of that x value. So the difference between those two y values is the change in y, the actual delta y. That's this distance from here, from that y value at f of a, all the way up to f of x. That's your delta y. So another way of writing this is to say delta y, or change in y, the change in the y values between x and a, is roughly equal to f prime of a times the change in x. And it's the same idea we were working with before with approximating the values, only now we're approximating the change in the y value as x goes from a out to a random x. What is the approximate change in the y values instead of what is approximately the y value. Okay, so this is an important equation, but how do we compute that, right? The idea is we want to approximate. Well, delta y, you can see here in the graph, delta y is roughly equal to dy. Dy being the difference between f of a and f of x on the tangent line at a. So dy is defined to be right here. Dy is the actual change between the two y values, at least on the tangent line. So dy is defined as, there we go, the derivative, the slope of the tangent line times the change in the x values, which you can call dx or delta x, it doesn't matter. So let's write this out. So dy is equal to the change in the difference of the y values on the tangent line, which is L of x minus L of a. L of x is this equation of that tangent line minus L of a is what you get when you plug in a here, which is f of a, and when you compute that out and you simplify, you basically get the slope times the change in x, which makes sense if you think about slope. So you get f prime of x times, you can call it delta x or dx, but for consistency I'm going to go with dx. And actually, if you think about it, the two derivative notations are the prime notation and the dy dx notation. If I were to divide both sides of this equation by dx, we'd get dy dx equals f prime of x, which are just the two derivative notations, okay? This is not really the point here, this is just an aside. But to illustrate that you actually can separate the dy and the dx, because that means small change in y and small change in x is equal to the derivative, or the slope of the tangent line. So that's where the dy dx notation can be really useful, is when you think of the derivatives in terms of changes in y and changes in x. Okay, but the point is that right here, delta y, change in y, can be approximated by dy, which is your derivative at a times the difference between the two x values. So delta, this is the big part, delta y is approximately equal to f prime of a times delta x. Okay, so we're going to use that to approximate the change in the y values. Let's bring that up a little bit. On this function f of x, which is a 9th degree polynomial, where x changes from 1 to 1.05. Okay, so if x changes from 1 to 1.05, then the difference between those values is your dx, or your delta x. 1.05 minus 1.00. So delta x is 0.05. The order is important. You do want to go right minus left, or larger minus, right minus left. X minus a, in other words. So that's the a value here, which I didn't actually state. So a is 1 because you want to choose an a value that's easy to compute the value of, where it's easy to compute the value of both f of a and f prime of a. So we're going to go with 1 for a as opposed to 1.05. That's much more difficult. Okay, so then we need f prime of a, so we need f prime of x. So the derivative would be 9x to the 8th minus 2. A is 1, so we'll plug in 1 to get the slope of the tangent line at 1, so that would be 9 times 1 minus 2. That's going to be 7. Okay, so the change in the y value as x changes from 1 to 1.05 is our delta y, is what we're calling it. It's approximated by dy, which is equal to f prime of 1, f prime of a, times delta x. So delta y is approximately equal to 7 times 0.05. So we just get 0.35. And that was easy to do without a calculator. So that estimates how much greater y gets. As x increases from 1 to 1.5, the y value increases on the function by about this much, by about 0.35 units, which of course you could use to approximate the actual y value like we did previously as well. And next we're going to approximate the change in the surface area of a spherical hot air balloon when the radius decreases from 4 to 3.9. If you were to actually compute the change in surface area, that would for sure require a calculator, although we'll need a minor one. That would require quite a bit of work, actually. So we're just going to use this approximation method, which is a bit quicker. So what is our function? Well, the function is surface area. So surface area of a sphere, you may have to look that up, but it is 4 pi r squared. Okay, so the change in the surface area then, delta S, is approximated by the derivative S prime at some value of A times the change in the radius, we're going to call delta R. Now, first off, which one is A? 4 or 3.9? I would say it's much easier to plug in 4, so we're going to use A as 4. That's the nice, pretty number, right? Easy to plug in. Okay, so A is 4, then delta R, you got to be careful here. Delta R is x minus A, or rather R minus A, actually. The random R value that we're interested in is 3.9, so it's 3.9 minus 4, so delta R is actually negative 0.1, and that negative sign is important because the surface area is going to be decreasing and R is decreasing. So delta R is negative 0.1. In order to find S prime of A, we're going to need S prime of R first. So bringing the 2 down, we get 8 pi R to the first is that derivative. So then we need S prime of 4 for S prime of A, plugging in 4 here, we get 8 times pi times 4, that's 32 pi. Okay, so let's approximate delta S then. So delta S, the change in the surface area, is approximated by the derivative S prime of 4, which is 32 pi, times the change in the radius, which is negative 0.1, or roughly, if you multiply that out and estimate it, it's about negative 10.05. Depends on your units. Let's see, we're in meters, so meters squared for surface area. So that's about how much the surface area would decrease by. And in this last example, we're going to approximate the value of this complex looking expression, we'll simplify it quite a bit, using differentials. So we're going to approximate the value of natural log of e cubed plus 0.1 minus the natural log of e cubed. Okay, so what we need to do is first define a function here. And what I'm looking at is I'm seeing a difference in two y values. This looks like a log minus a log. That's like a y minus a y. So that's why this is differentials. We're estimating the change in the y values. In other words, the difference in those two y values. So our function must be natural log of something. So we're going to go with natural log of x. And the x values that we're going to plug in are e cubed plus 0.1 and e cubed, which means it pretty much tells me my a value. If I use a as e cubed, then this is like the natural log of a, and this is the natural log of a plus 0.1. The 0.1, that's the difference between the two x values. So my other value, the x that we're going to use here, is going to be e cubed plus 0.1. Right, so that would be my natural log of x minus natural log of a. I'm estimating the change in the y values, let's write that out, as x changes from a to x. Okay, this is a good choice. E cubed is a good choice because we can compute the natural log of e cubed pretty easily, and its derivative as well. Let's go ahead and compute the derivative there. So f prime is equal to 1 over x. Okay, so using differentials then, we know that the change in y values, or I'm going to write delta f this time, is roughly equal to f prime of a, or in other words e cubed, times x minus a, which is e cubed. That's my delta x. Actually, I could have computed delta x up here. Clearly the difference between those two values is 0.1. So the change in the y value there is roughly equal to 1 over f prime of e cubed would be 1 over e cubed times 0.1, or 0.1 over e cubed. Let's see what that approximates to. Okay, it looks like I'm getting 0.004978 right there. As the approximate value of that expression based on differentials. So let's see what the actual value is. Okay, so this is the value of the natural log of e cubed plus 0.1. Natural log of e cubed is 3, so if you subtract 3 from that, you get 0.004966. That's pretty close, 0.0049. The first 4 decimals are the same. This is only off by a little bit 1, so you're very, very close approximation there. And that's it for this section on linearization and differentials.